Hey everyone, and welcome back to a new Manim with Ease episode. This one will be a bit different than the previous ones, as instead of doing the usual thing and going over a bunch of different scenes to explore one particular topic, today we will discuss one particular scene which we will use to mainly illustrate a bit of useful math, some linear algebra, while also revisiting a bunch of topics discussed in prior episodes. So in a sense, this episode is a explain this animation kind of episode. As usual, check the video description for a link to my GitHub with all of the code of this episode, as well as links to further useful resources. To be more precise, we will talk about strategies to decide whether a point is inside or outside of a shape, and we'll also discuss some math to determine which side of a straight line we are on with a point. We'll also learn a bit about how vectorized Mobjects are built internally, and once again we'll revisit updater functions. Here is the animation that we are going to discuss as output by Manim, that is, no post-production or anything has been applied to it. Let us unravel the two main ingredients of this animation. On the one hand, we have points becoming opaque as soon as they are inside of the growing circle. And on the other hand, we have points that change their color depending on which side of the line they are on. Now let us look at the concrete implementation. After some imports and the usual scene class header, and the first thing that happens in the construct method is that we instantiate both a circle, growing circle, and the line called moving line. For the moving line, we then assign a normal vector attribute by copying the moving line, rotating it about 90 degrees, and then calling the getVector method, which gets the directional vector of the line, which is the difference of the endpoints of the line. We then define two functions, the opacity updater and the color updater function, where the opacity updater checks whether the dot is inside a circle. We'll talk about details in a moment. And if it is, it sets the fill color of the dot to blue and its opacity to 1. It clears all updaters, which in particular removes the updater that is currently running. It adds another updater, the color updater, instead. And we also play the sound that you've heard in the video that played earlier. The second updater, the color updater, works similarly. It checks whether the point is on the left of the line or the right of the line. Again, we'll talk about details, the mathematics of it in a moment. If it is on the left, then we check whether the color of the dot already is blue. And if it is not, that is, if the dot is still yellow, then we set the color to blue and play again a sound. And otherwise, in case the point is on the right side of the line, we check whether the color is something other than yellow, which means it's blue. And if that's the case, then we set the color to yellow and again play a sound. This is what takes care of the changing colors. The rest of the scene really isn't that exciting, so I actually want to talk about that also a little bit later. What I think it's much more interesting is how the two updater functions work and how the mathematics behind these checks works. So let me switch to pen and paper, at least the digital kind, to discuss that in more detail. Here's the first problem I want to talk about. In order to check computationally whether a given point is inside or outside of a circle, here's the default approach that you usually pursue in this case. Consider this situation. We first determine the current radius of the circle, and we do that by taking the difference between some point on the circle and the midpoint, so that we get this vector pointing from the center of the circle to the point on the circle, and then we determine the length of this vector. And this vector r, the length of this vector, will be the radius of the circle. And we do the exact same thing, just with the reference point. So we determine if our reference point is here, maybe, Then we determine this vector over here, let's call it V, as a difference between the reference point and the center of the circle. And all that we need to do now is compare the length of these two vectors. To determine the length of the vector, we use Pythagoras' theorem, meaning that we consider the x component and the y component. These span a right-angled triangle, and the square of the length of the diagonal can be computed as the sum of the squares of the two sides of the triangle. So in this case, we would get that the square of the length of v is the x component of v squared plus the y component of v squared. And same for the radius. The square of the radius is the x component of the radius squared plus the y component of the radius squared. And all that we need to do now is compare these two. Namely, if the red quantity, the distance to the reference point, is less than or equal to the radius of the circle, then we know that the point is inside. If, on the other hand, the distance to the point is larger than the reference, than the radius of the circle, well, then the point has to be outside. And this exact computation is exactly what you saw earlier in the code as well. Let's take another look. We are inside the opacity updater, and we check this condition here. And what happens here is we take the difference of some point on the circle, which is the first point in the points list of the circle, and the center of the circle. We take the difference of these two, we square the vector, which in NumPy squares every entry, and then we consider the sum of these. And on the other hand, we determine the difference between the center of the dot and the center of the circle, so that's the red arrow from before. And again, we square these and sum it up to get the square of the distance to the reference point, to the dot. This strategy works reasonably well as long as the shape that is growing is a circle. So as long as we need to decide whether something is inside or outside of a circle, and that's because the parametric equation of a circle is relatively easy and works well with comparing distances. But what if we have a more general shape? So what I'm interested in now, and I realize this is a sort of academic question at this point, but I'm interested in not the question when a point is inside of a circle, but rather what can we say when we have a general shape? So instead of having a circle, what can we say about when is a point inside of a general closed curve? To answer this question, there is a very cute idea that I would like to briefly explain. And this will also lead us to a short digression on how vectorized Mobjects in Manim, so pretty much all the shapes that you add to the scene and that you display on the screen, how these are actually rendered internally, or at least how they are represented internally. The tool that we are going to use for this is the so-called winding number. So here's the example that briefly illustrates the idea behind it. Consider the following shape, the following closed curve, and one point that's, well, let's say inside of it. The idea of the winding number, or the idea how Manim implements determining the winding number, is as follows. We take a sequence of points along the curve. I won't space them out so evenly, just a few points. And then we iterate over pairs of these points. And what we do is we always measure the angle between the two neighboring points and the reference point, which means that we have some angle over here, there is some angle over here, there is some angle over here. And I draw arrows in these angles to signify that these are oriented angles. If we would measure in the other direction, so counterclockwise, then this would be a negative quantity. But as long as we go in that direction, everything's fine. We measure and measure and measure. And in the end, you will see we have measured all of our control points, and what we get is well, a full 360 degree or 2 pi angle. So in case we measure these angles and we get something that's full rotation, we know that the point has to be inside of the shape. So let me put that down. Observe sum of angles equals 2 pi, and we know point inside. Because, and this is the other direction for this concept. If we would take the exact same shape, exact same idea, but this time we move our point outside of the shape. So let's say we move it somewhere over here. Then what happens with the angles? Let's see. We take 2 and 2 as before. We have this one and this one. This is measured in this direction, so positive. This one and this one, still positive. This one, well, also still positive, but getting hard to draw. Then we have this one here, still positive. But now we move in the other direction with the angle. So the first time that something weird happens, so to say, is this angle down here. I'll draw it in red, between this point over here and this point, because this one is now measured in counterclockwise direction, which means that this actually subtracts from the angle that we have from this sum that we have already collected. The next few points do exactly the same. This one is also negative. This one is also negative, and you can see that the idea here basically is that these angles, after you collect all of them, they cancel each other out because, well, you did not go a full rotation around the point, because the point is not inside of the shape. So if we find that the angle, sum of angles is 0, then we know that the point is outside. And this is a quick and easy idea for determining the winding number. Just take a bunch of points and then measure the angles between the points and the reference point, and then decide, based on what result you get for the sum, whether the point is inside of the shape or outside. Let me also mention that the way we do this here is actually just an approximation of the actual curve, because we take discrete control points along the curve and we don't integrate over everything. This is what we would need to do if we would want to have a mathematically correct result that captures the exact result for all points inside and outside the curve correctly. In our case, the approximation with discrete control points works reasonably well, though, so there's no need to resort to heavy machinery. In our model, results might be wrong if we pick a point in this border region, so to say. So if we have shape and we chose some control points, say here, let's actually just draw 3 control points, then there is an imaginary polygon here, which we use to approximate the curve. And if we choose points from this region here, or from this region, or from this region here, in this case, the winding number strategy from before will fail and yield an incorrect result, because the control points have not been spread finely enough. Now we know about the winding number. All that we need to do now is to have some sort of practical approach to how we can actually use it in Manim, which means that we need some way to choose a bunch of points, a bunch of control points on our shape. And if we know a little bit more about how vectorized objects in Manim are actually represented, there is a more or less easy choice. So you can do whatever you want with the points. As long as you choose a bunch of points along the curve, you will be fine. what I suggest is we could use the so-called anchors of the Bézier curves that make up the object itself. So let me briefly explain a little bit about that. What are actually vectorized objects? For the Cairo renderer, vectorized objects are built from so-called cubic Bézier curves, which means that if we look at their points attribute, this will always be in groups of 4 points. And these 4 points, each of these 4 points determine exactly one of these so-called cubic Bézier curves. And this is how this works. The first point in such a group is an anchor. We'll draw these with a red cross. Then there is a handle, which is attached to the anchor. Then there's another handle and another anchor. And again, the anchor is attached to the handle. To determine the Bézier curve from these 4 points, we use something that's called the Castellios algorithm. And this works as follows. We draw an auxiliary line between the 2 handles so that we have 4 points that are piecewise connected with a linear function. And then what happens is we subdivide each of these curves at the same ratio. So for example, we after 10% of each of these lines, we draw we mark an extra point on the curve. So there would be 10% here. Let's say this is about 10% here, and this is 10% here. We draw new auxiliary lines between these 3. One, this is the other one. Now we forget about the old construction and focus on the new one. We do the same with these 2 lines that we got just now. So we subdivide them again, these 2 pieces, at 10% each. That we have one auxiliary dot here and one auxiliary dot here. We connect 2 and just one line remains. We can forget about the previous construction again. And for this new auxiliary line here, we again mark the 10% mark. There's nothing else now that we can subdivide, and this here is actually one point that will be on the curve. We do it for, well, any value of t, such that we can separate between these curves. What we will get in this case is something that looks a little bit like this. Well, and what you're seeing now is a simple animation that shows how the Castellios construction works. The separation ratio, so the point at which these auxiliary lines are split, grows from 0 to 1, and by tracing the position of this red dot, the final point in the construction, we obtain the actual Bézier curve. Let me give you a practical example for how exactly shapes in Manim are built from Bézier curves. Let's consider a circle. So I'll just create a standard circle with radius 1, and then look at the points attribute of this circle. And as you can see here, there are lots of points on there, but not all of them will lie on the circle. As you can see here, this is the point 1, 0. I'll ignore the third coordinate. Looking even more closely, we will see that this here is an anchor, so this is on the circle. These 2 are handles, so these are not on the circle necessarily. And this here again will be another anchor, which means that it's again on the circle. And actually, if you look into the value, that's 0.707 and so on. This is 1 over root 2, so this is exactly the point on the diagonal. If you imagine this, or if you look into this some more, you will actually see that a circle in Manim is made out of 8 such cubic Bézier curves. Let's verify. Look at the length of circle.points, and we'll see it's 32. Dividing those by the groups of 4, so that the circle is made out of 8 Bézier curves by default. Now I understand this is a very hasty and not very precise introduction to Bézier curves, but there are excellent resources out there which can explain Bézier curves much better than I could in this intermission here. I leave a link to 2 resources I like in particular. There's a brilliant video by Freya Holmer, and there's also an open source book by Pomax in the description of the video. And to leave a little bit of shameless self-advertisement in this video as well, I've recently published a deep dive into Manim's internals, distilled somewhat from the renderer tour stream that I did on Twitch a while back ago. The video of that is also still available on my YouTube channel. This is now a new thematic guide in Manim's documentation, and I'll leave a link to that as well. It goes very, very deep and explains thoroughly how exactly the internals of Manim, at least for the Caillou renderer, work. And now all that remains to be done is to actually implement this approach in Manim. Here's how I would do that. I'll comment out the previous comparison of the distances, and to get the winding number of some reference point, there's a function already implemented in Manim which is called conveniently getWindingNumber. However, the winding number, this function only returns the winding number of the origin. So in order to determine the winding number of some reference point, we need to shift the points of the shape accordingly. In other words, we take our moving circle, the growing circle, we take the anchors of the circle, get anchors, we subtract the reference point, which is our object dot get center. Now this returns the winding number of the reference point. So this will return whether we wind around whether the curve winds around the reference point once or 0 times or whatever. So we want to check whether this is greater than 0, or actually not equal to 0 would suffice. But well, here we go. And because the getWindingNumber function is not necessarily numerically stable, because there are lots of tiny additions and subtractions that are about equally large in size, it can happen that you're slightly off an integer numerically. So there's a slight rounding error from time to time. But it doesn't matter, you can just use the round method to actually get an integer out of that. So I use round of this, check whether this is greater than 0. And then this is how I would implement a winding number based check on whether or not a point lies inside or outside of a shape in Manim. Alright, there we go. That explains how the opacity updater works in detail. Let's move on and look into the second part, the color updater. To make the color updater work, we need to figure out whether some point in the plane is on the left or the right, one side of the line or the other. We can actually do that computationally without much effort if we just revisit some linear algebra. And here's how we do that. A straight line, as I've already prepared here, can be described in its parametric form with the following consideration. Any point on the line, let's take this point x here, can be reached from some fixed point on the line. Let's take this point p here. Then we also need a directional vector on the line. Let's call it v. That's this one over here. And adding a scalar multiple of this directional vector to the fixed point, we can eventually reach our point x. So in other words, we can write the parametric form as x can be written as the fixed point p plus a scalar multiple of the directional vector of the line. By taking the directional vector and rotating it about 90 degrees, we can get a normal vector of the line. So this would be this one over here. And what we can do now is we can take the parametric equation and we can form the dot product of both quantities on the left and the right hand side with this normal vector. Meaning that we would get something like this. We have the equation from before, we multiply dot product with the normal vector on the right equals point, fixed point on the line times the normal vector, again dot product, plus the scalar multiple times the directional vector times, again, the normal vector. And as a property of the dot product, whenever two vectors are perpendicular, and we take the dot product of those two, then the dot product actually yields 0. So this means, in this case here, that this term over here, this here is 0, which means that this equation here, after multiplying with the normal vector, results in xn equals pn. And this equation here is what is known as the normal equation of a line. This is a very useful equation. It tells us that the dot product of any point on the line with the normal vector of the line will yield the same number. This here on the right hand side, Pn. The neat trick that allows us to easily tell whether a point is on one side or the other side of the line comes from exactly this equation. Because here's what happens. If we take any point on the line and form the dot product with the normal vector, then we get the same number. If we now choose not a point on the line, but say we walk from the line in the direction of the normal vector somewhere in this half plane, so say we choose this point Q here, then the number, instead of this Pn, which we had before, Qn would be larger because we moved in the direction of the normal vector. And likewise, if we move to the opposite direction, so somewhere on this lower side, this half plane here, then this number would get smaller. Let's illustrate that with an example. Consider we have the line with normal vector 1, 1. So let's briefly draw a coordinate system. Something like this. And I want to have the normal vector 1, 1. So this should be my normal vector, which means that the line, let's make the line go through the origin, that's fine. The line would be, say, this. The directional vector is on there, that's fine. What's the equation of this line now? So this is 1, 1. Well, the normal vector equation was xn equals pn, where p is a point on the line and x is a general point, so to say. So this translates to xy with the dot product with 1, 1 equals 1 point on the line, which in our case we can take the origin, so 0, 0, with the dot product with the normal vector 1, 1, and that gives x times 1 plus y times 1 equals 0 times 1 plus 0 times 1 equals 0. So x plus y equals 0 is the normal vector equation of this line that we have over there. And now let's check that this property with walking towards the normal vector in the other direction of the normal vector checks out. So here's what we need to observe. If we take a point 1 on the line, then the result should be 0, because that's the right hand side in our normal vector equation. Let's check. Let's take some point over here. This point, for example, over here is on the line. That would be something like minus 2, 2. So if we take minus 2, 2, and we take the product with the normal vector dot product, then we get, well, minus 2 times 1 is minus 2 plus 2 times 1 is minus 2 plus 2, and that's 0. Checks out. Okay. Let's try again, this time with... Let me actually move this. Let me actually move this check so I don't disappear behind it. Now let's take another point somewhere from the upper half plane, let's say. Let's take this point, Q, over here. This would be 1, 2, 3, 4, 1, 2. So this would be the point 4, 2. 4, 2. And if we take that, so upper half plane, like our point 4,2. And we take the product, the dot product with the normal vector again. 1 equals 4 times 1 plus 2 times 1 is 6, which is larger than 0. And this makes sense because the point is when looking from the line in the direction of the normal vector. And on the other hand, if we take some point that's on the other side of the line, so on the lower half plane, that's number 3. Say, for example, we can take this point over here. That would be minus. That would be 1 minus 2. So let's say we take the point 1 minus 2 with the normal vector. That's 1 times 1 is 1, minus 2 times 1 is minus 2, 1 minus 2 is minus 1, and that's less than 0. So you see, depending on where we are with the point, whether we are in the half plane that's in the direction of the normal vector, or whether we are in the half plane that's in the opposite of the direction of the normal vector, the result on the right hand side will either be larger than the number from the normal vector equation or smaller. Let me just say, the fact that this strategy works in the example we just saw obviously is not a general proof of this property. It's mainly here to give you some intuition. However, the proof isn't much more complicated than that. Effectively, the ingredient that you need to prove it is the so-called normal projection. The number resulting from the dot product of some point in the plane with the normal vector measures some sort of displacement of the point in the direction of the normal vector. All points on the line have the same displacement, which is why the normal vector equation looks like it looks. The points with more displacement lie in the half plane that's in the direction of the normal vector, and the points with less displacement lie in the other half plane. That means, summing everything up, to decide on which half plane a point lies on, we simply compute the dot product of the point with the normal vector and then compare the result against the number in the normal form equation. We are back in the code at the implementation of the color updater method, and the comparison with the dot products actually happens right here in these two lines. What we do is we compare whether the dot product of the current center of the dot with the normal vector of the moving line is less than some point on the line times the normal vector. And what we briefly need to think about is in which direction does the normal vector of the line point. When initializing the line, I drew the line from -7, -5 to 6, 5, which means the line grows from the bottom to the top. And if we go and rotate this by 90 degrees, then the line will point, or the direction of the line will point to the left actually. So this means that if the displacement of the center of the point of the dot is less than the displacement of the point on the line, this means that we are in the half plane on the opposite side of the normal vector, which is the right side of the plane in this case. The dots on the right side should be blue, and we check that. If the color of the dot is not blue, then we set it to blue, because that means that the line just swept over the point in the other direction, and play the sound. And in the other case, when the displacement is larger, which means that we are in the half plane that's in the direction of the normal vector, then we are on the left side of the line, and these points should be yellow. So we check whether that's the case. If it's not, then the line just swept over a point. We need to set it to yellow and add the sound. And that's really everything the color updater does. And well, that's all the mathematics that we need for all the bits and pieces from this animation. The remaining code is actually not really that interesting. Basically, add the Mobjects to the scene, first the growing circle, and then in a for loop we create a dot with lower fill opacity. We move it to a random position and then add the opacity updater to it. In the end, we add it to the scene. Do that some number of times. You can also increase that or decrease that number if you'd like. And the actual animations in this scene are rendered from these 4 play calls. We animate the growing of the circle by scaling it to fit some width. We play the creation of the moving line, and then we just shift the moving line in the one direction, and then we shift it back. And that's all there is to it. All of the magic of this scene happens inside the updater functions. And well, this concludes this episode. As usual, I'd appreciate your feedback in the comments down below. Has this been useful to you? Should I discuss more mathematical foundations for animations in future episodes? Are there more Manim concepts you'd be interested in? Leave a like in case you enjoyed this video or found it helpful. And if you feel like watching more content like this in the future, then make sure to subscribe to my channel. And with that, thank you very much for watching, and see you in the next one.